Hello everyone. In today's lesson, we're going to be covering section 2.1, which is going to be on exploratory data analysis, specifically histograms. So first let's talk about exploratory data analysis, or EDA. Exploratory data analysis is a critical first step in analyzing data from an experiment, mostly as a graphical approach. This is actually one of the first things I do anytime I get data. And this is how you kind of get a feel for the shape of the data, what trends there might be, and anything that you can actually glean from the data when you get some data that you don't really understand until after you've done this step. So the main reasons we're going to use exploratory data analysis is to get an in-depth insight into the data set itself. We also will do it to understand the behavior of the data, to detect mistakes or outliers in the data that might exist. This will also allow us to check assumptions. This will allow us to extract important attributing variables and to determine if there are any relationships among our explanatory variables. So let's briefly talk about each of these. So first, to get in-depth insights of the data set. So this would be things like figuring out its distribution, its skew, whether it's univariate or bimodal, normal, things like that. They'll help us have a better understanding of the data set. This could be, again, things like its distribution, whether it's normal distribution, whether it's skewed, whether some data is constantly increasing or decreasing, or whether it's cyclical, to detect mistakes or outliers. Now, we're actually going to talk about this briefly in a few slides, but we're always going to be looking for outliers in the data. And an outlier is just some data that doesn't fit the rest of the data. And we'll talk about a few reasons why that might be the case, but sometimes your data exploration will actually help you determine if you have any outliers or anything like that. Next is to check assumptions. In everything we do in statistics, whether it's modeling, it's doing some sort of hypothesis test, confidence intervals, whatever we do, there will always be some base assumptions. And data exploration will actually allow us to determine whether those assumptions are probably true or not, or at least appear to be true. To extract important attributing variables, this could be things like finding correlation, and this also goes with the relationships. We do correlation coefficient, we could do some sort of correlation graph where we determine that two variables are highly linked together, things like that. So one of the most common methods that we use when doing exploratory data analysis are histograms. Now, histograms are kind of like bar charts, where a bar chart, we usually have vertical bars. They don't have to be vertical, they can be horizontal. But in a bar chart, you will have these bars which represent different groups or categories generally. So this might be something like group A, group B, and group C. But notice in each of these bars have a gap between them that represents some separation from group A to group B. You're either in group A or you're in group B, and there's nothing in between them. You fall into one or the other. So these are really great for categorical data. Histograms, on the other hand, are going to be graphs where there is no space on our interval. So it'd be something like this. And this means that you could actually think of this as an interval of data from some starting point to some ending point, where any data point in between has somewhere that it could fall. Meaning that in the bar chart example, if I wouldn't have any values that fall here, this is why it'd be something like categorical, right? If we were talking about colors, this could be green cars, blue cars, yellow cars. For histogram, this is great for interval data or ratio data, which means that it's basically real data that actually falls in a spectrum of possibilities. Meaning that I have to have no space because something has to be able to fall into this group or this group. So with these graphs, and this is true for any graph, you always want to make sure that it includes some specific things. Specifically, it should always have a title. So in this case, I don't know, we'll just call it our histogram. But generally what you're going to want is you're going to want this to be something that is relevant to what the graph is. That way, if somebody were going through something that you created, some sort of presentation or academic article or whatever you're doing, they could quickly see, what does this graph represent? Now, of course, I'm using generic terms like bar chart, histogram, because we don't actually have real data that we're making this graph for. Your x-axis is this horizontal axis at the bottom. So you want to label this as well, because this is going to tell you what your data is changing over, right? So as we go from left to right, what does this represent? Heights, income, things like that. Your y-axis is going to be the vertical axis on your graph. And this would be labeled generally with what is the change in y representing. Now there's 4 types of histograms we'll look at in this class. Histogram, which is actually a relative frequency histogram, cumulative frequency histogram, relative frequency histogram, and cumulative relative frequency histogram. Okay, but you want to make sure, no matter what type of graph you're doing, that you always label this. So if somebody were flipping through, they could quickly discern what does this graph represent, what does this x-axis represent, and what does my y-axis represent. And this is one of those key places where oftentimes people will try to manipulate what something is showing in order to sell some message, right? For example, in your x-axis, you should have scaling that makes sense for your data, right? So I'm sure there's times you've seen where someone comes on and shows something like, oh, look, the market's crashing, it's going down, 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 and it looks terrible. You're thinking, oh my gosh, everything's going terrible, we've lost everything. But if you were to just pull back just a little bit, you might see the scale of this is actually something where it's been increasing, and yet they focus so much on this little part right here to sell a certain message, whether it be this thing is causing everything to crash, or maybe someone else focuses right here, look at how much, we were growing at that point. Whereas if you look at the overall trend, it might be upward, but by focusing on this, you could show that whatever's happening right now is causing a downward trend, which isn't necessarily wrong, but the way it gets kind of shady is when you don't properly label your axes. People should be able to look at your graph and easily discern, what does this mean? What is the scale on this graph? What does this x-axis represent? Is it time in seconds, minutes, days, hours? That's going to drastically change what the view of this graph looks like. Okay, so a couple things about histograms. Before we get into details, we should keep in mind that the goal of a frequency histogram, or just a histogram, is to plot a data in a meaningful graph so that we can look for a pattern in the data. So kind of if we were to look at this graph that I drew here, if I kind of were to draw like a line kind of going through it, I could get an idea of the shape of the data. And if I were to get rid of these bars, just pretend the bars aren't there, I can get an idea of what the shape of this data looks like. It also could allow me to look for outliers, where an outlier is just a value that's very different from the rest of the data. So that might be something like you have some data out here, where there's nothing here, but then suddenly you have some data out here. This is an outlier. Now, an outlier does not necessarily mean that this information is incorrect and you should cut it. An example of this would be, let's say that our x-axis represents the net worth of Americans, and we're doing a study where we want to know what people's political views are, and we're measuring by their net worth. Well, most people will fall into this bracket here, but then you're going to have a select few individuals, these multi-billionaires who make so much more than the norm that there's almost this huge gap between the normal person's net worth and this exceptional value right here. Now, if I'm viewing the political views of all Americans, this data is perfectly valid. So it doesn't mean that I should just drop this. But sometimes one way you might be able to drop it without actually just dropping it because it's inconvenient is reframing your question or your whatever it is you're looking at. So this might be something like, I want to know what the views of Americans are that have net worths between $20,000 and $140,000. Maybe you kind of give yourself a more limited window where you only look in a certain area. So these values would be cut out just by the fact that we're not looking for those who are on the extremes, both positive or negative, of the normal data. Now, when you're looking at outliers, it could also be that these are mistakes. For example, if I'm putting grades into Canvas and I put in a grade 744, it's going to flag it because it knows that the grade should be between 0 and 100, meaning that if I have a grade that is beyond 100 with some threshold, right, because it might take into account there's bonus points, maybe it goes to 115. But if it sees some value that's so far outside of it, it flags it because it's saying, I don't think this makes sense. This might be incorrect. And it would be right. If I put a 744 for someone's grade, it's likely that I typoed. I probably hit 7 and then double hit 4 instead of just hitting one time. So an outlier is just some data that is far out from the rest of the data. And a histogram can give us this information by kind of showing us that we have these values that are far outside of what we would expect. Just on this point, it's kind of like a joke that people used to tell where it's if you took the average income of everybody on a bus and then Bill Gates walked onto the bus, suddenly everybody becomes a millionaire. It's because the joke being that if you have like 40 people whose average income, let's say, is $60,000, well, having one person with many billions of dollars would suddenly knock everybody up. If you took the average income of everyone on the bus is over $1 million. Obviously, he didn't change the income of anyone on that bus, but it's because he is so far outside the norm that he would pull the average up tremendously. The other thing I wanted to briefly talk about with these histograms is to kind of reiterate that these are extremely useful. This is actually one of the first steps that I'll take when I get new data to get an idea about the shape. And it's super easy. For example, if I'm in R, if I have the data, all I have to do is just put hist, parentheses, and then whatever data I have, and it will create a histogram for me so I can quickly see the shape of the data. Now, let's talk about the types of problems you might see when we're doing a histogram. So the main two types of problems you see are going to be where you're going to have the raw data or where you're going to have a partially filled out table. And really, I would say there's actually kind of three parts. There's raw data with a partially filled out table, and then there's problems where you have none of the raw data, you only have a table. And which one of these problems you're doing will actually determine what steps you need to do to complete the table to create your histogram. Now, this actually is something you will encounter in real life, because for example, generally, if I do a study, I'm going to have the raw data, meaning that I can create whatever histogram I want from scratch exactly how I want it. But let's say that I go grab some data from the census or the Federal Agency for Fish and Wildlife or something like that. Generally, I'm not going to have that raw data. I'm going to have a pre-filled out table, meaning that I won't know what the individual outcomes are. I only know what the group outcomes are. And this will, of course, affect what I'm able to do with my histogram. Now let's talk about that data. But before we do, let's first put this table up on the board. Great, now we have our table up. So this is called a frequency table. And this frequency table will include two things for every frequency table, which we are going to be expanding to create our histogram table. But first we have our class and our frequency. So the first column is our class. And you'll notice we have the class 3 to 8, 9 to 14, 15 to 20, and 21 to 26. This would represent those intervals that our data can fall into. F, which represents our frequency, is how many of our data points fall into this interval. So that means that 2 of our data points fell into 3 to 8. They could be something like 4 and 7. 6 values fell in 9 to 14. 7 values fell in between 15 and 20, and 5 values fall in between 21 and 26. And then, of course, at the bottom we have total, which means we have a total of 20 total data points that we put into this table. Now, this is what I was talking about. If you have a pre-filled out table, I don't know what these two values are. I just know that there's something between 3 and 8. Now, if I had the raw data, which would look something like 4, 6, 12, 13, 17, 9, 11, 12, something like this, then I would actually know what the individual outcomes are, and I could create this table. And I'll show you how to do that afterwards. But if all you have is this table, then all we know is these two values are somewhere between 3 and 8. They could both be 3. They could both be 8. They could have one that's near 3, one that's near 8. They could be somewhere in the middle. We don't know what those values are. And we'll talk more later about what we should do in that situation for certain calculations. But for now, let's focus on the actual frequency table, which has our class and our frequency. Now, a couple things that we want to think about when we're looking at this data is first we have our data count, which is I. So I equals 1, 2, 3, up to n. Now, this I just stands for an index, which means that it is which data point. So I equals 1 would be the first data point. I equals 2 means the second data point. I equals 3 means the third data point. Up to I equals n, the nth data point, which if you remember from our prior lesson, little n just represents our sample size, or how many data points we have in total. So this means that each of these is just indexing to tell us which thing are we looking at. So next we have the outcome of our data. So if we have x sub I, all this means x is just a way that we represent an outcome. So x sub I means the outcome for index I. So for example, x1 would be the first outcome. So based on the numbers I wrote, that would be 4. x2 would be the second number I wrote. That would be 6. x3 would be the third outcome that I wrote, 12. And then x sub n would be the last data point. Let's say that it's 22. So this just represents x is the outcomes. xi is x1, first outcome, x2, second outcome, x3, third outcome, up to whatever nth number you have, your last data point. Okay, so now in our graph, our frequency table, we have our classes and we have our frequency. When we're actually creating a histogram, we actually are going to have some other columns to flesh out our actual graph information, but also for the different types of histograms. So specifically, we're going to be looking at frequency, relative frequency, and cumulative relative frequency. So there's 3 main properties of histograms that we need to talk about. The first is that your classes must be continuous. So there should be no gaps in the numbers in our number line. So there should be no gaps in our number line, even if the class has nothing in it. So for example, here we have 4 classes, all of them have something in it. You can have a class with 0, but we would still represent it as there being a class or group for that interval. Now, one thing you might notice if you look at our frequency table is we do have gaps, right? If I were to draw this out, this would be from 3 to 8, 9 to 14, 15 to 20, and 21 to 26. So we have gaps in our line interval. So we're going to have to actually fix this before we can create a histogram. Because right now we don't have an interval from the lowest value to the highest value with no gaps. So we'll cover that soon. The next property is that the classes must be exhaustive. That is to say that if I were to have all my data, then every possible value I have has to be able to fall into one of these intervals, starting from the lowest point to the highest point. That means that if I were to take some data in, there's nothing that could either fall below the lowest point or above the highest point. And then the last property is that our classes must be equal width, right? So if we look at the distance between each of these, they will have the same class width, which we'll define how you can determine that in a little bit. Now, there is an exception to this. The exception is sometimes at the upper or lower ends of our graph, we may actually do an open-ended interval. Something like if we're doing ages, we might say every 20 years. So 1 to 20, 21 to 40, 41 to 60, 61 to 80, 80 plus. And this is usually done when you have sort of this, you're going to get less and less data as you go out, but also you don't want to have too many classes. Because if I were grouping people by 20-year age differences, then there might be a certain point where now I've got so many classes, it kind of distorts what I'm trying to show. So what I might want to do is I might want to lump all the people beyond a certain age into one group. Or you might do the same thing at the lower age, right? You might say something like, okay, we're going to look at 6-year increments, but really we're kind of starting at 24 years old. So everything else is going to be less than 20, something like that. It could be for anything, but generally we want them to always have the same width. And there's actually some really cool properties we get because of that, which we'll talk about in a few minutes. So when we come back in the next video, we will go into how do you find all this stuff, including the class width, how do you expand this to be one constant interval, and what advantages we get by these all being the same class width.
Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.